Physics, May June 2014, Part 5. Question 30. A battery of electromotive force V and negligible internal resistance is connected to a 1 kilo ohm resistor as shown. So there is 1 kilo ohm, it's connected. A student attempts to measure the potential difference PD across the point PQ using two voltmeter, one at a time. The first voltmeter has a resistance of 1 kilo ohm. Sorry about my writing. And the second voltmeter has a resistance of 1 mega ohm. What are the readings of the voltmeter? So you can see there is an e.m.f. with negligible internal resistance. It's connected to a fixed resistor 1 kilo ohm. And here in place of this junction PQ, we can connect two voltmeters one at a time. So one voltmeter has 1 kilo ohm resistance, the other one has 1 mega ohm resistance. We need to know the voltmeter reading. So in case if you attach first voltmeter which has 1 kilo ohm resistance, then you can see that the same current passes through. This is the positive terminal of the battery, so current passes through the positive terminal to the negative terminal. So same current passes through this resistor as well as the voltmeter. Therefore, they are connected in series. This voltmeter is connected in series with 1 kilo ohm resistor. So as you can see, both of them have the same resistance. The voltage will be equally shared. So this resistance will have voltage V over 2, PD of V over 2, and this voltmeter will have PD of V over 2. So we need to know the reading of the voltmeter with 1 kilo ohm resistance. It's V over 2, V over 2. V and V, so C and D is not the option. Now in place of this voltmeter, they removed it and they connect 1 mega ohm resistor. So what happened is most of the voltage will be given here. That means more energy is required by the charge to move through this voltmeter. So mega is 10 to the power 6, kilo is 10 to the power 3. So you can see that most of the voltage will be spent, or most of the PD will be supplied to this voltmeter. So since this value is high, we can assume that almost all the PdV is given here. So as you can see, reading on the voltmeter with 1 mega ohm resistor, it's definitely not going to remain the same. It's going to increase to an amount which is equivalent to the e.m.f. Therefore, the answer for this question is option B. Question 31. A copper wire is to be replaced by an aluminium alloy wire of the same length and resistance. So same length, same resistance. Copper has half the resistivity of the alloy. So the best way is to draw the table. So here this is aluminium alloy, this is copper alloy, same length, same resistance, but we have seen that copper has half the resistivity of the aluminium alloy. So if I take the aluminium alloy's resistivity as a rho, then copper will have half of it, which is rho by 2. The equation that connects resistance with resistivity is R is equal to rho stands for resistivity into length divided by area. Now the question is, what is the ratio of diameter of alloy wire to diameter of copper wire? So let's make this equation in terms of diameter. So first thing is I take this area as my subject. So I get A is equal to rho L over R. Now since it's a wire, the area is going to be pi r square. Radius is half of diameter, so d by 2 whole square. I get pi d square by 4. So pi d square by 4 is equal to rho L over R. Taking d square as the subject, I get 4 rho L over pi R. Now let's make this equation for the aluminium alloy as well as for the copper. So if I take for the aluminium, diameter of aluminium square, because there is a square here, is equal to 4 into resistivity. Resistivity is rho here. Into the length remains the same. Here I have considered L divided by pi R. Let's call this as my equation 1. For copper, I'm doing the same thing. In place of resistivity, I have resistivity over 2. So I've just substituted all the values. Now the easy way is to divide equation 1 by 2 in order to cancel the common terms. So you can see there is 4 here, there is L here, there is R here which is common, pi here, there is a rho here. So now I get an equation, aluminium over the diameter of the copper, which is whole square, is equal to 1 over, this 2 remains as it is, 1 over 2. So reciprocating, I get 1 over, reciprocating 1 over 2 becomes 2. So the diameter of aluminium over diameter of copper, take the square to the other side, it becomes root 2. So the answer for this question is option A. Question 32. The diagram shows an electric pump for a garden fountain connected by an 18-meter cable to a 230-volt main electrical supply. The performance of a pump is acceptable if the potential difference across it is at least 218. The current through it is then 0.83. So the main supply provides 230 voltage. The pump can work with a minimum voltage of 218. When it is 218, that time the current is given by 0.83 ampere. It is connected by 2 cables. You can see one is 18 meter. The other one is also 18 meter, 2 cables, because the circuit has to be completed. As you can observe, the same current passes through the entire circuit. That means this entire circuit is in series. The arrangement of this circuit is in series. What is the maximum resistance per meter of each of the 2 wires in the cable if the pump is to perform acceptably? They're asking what will be the resistance over the length of this cable, not cable, wire. So first thing is we need to find what is the voltage that is given to this wire. Now out of 230, since it is connected in series, we are taking 218 volt for the pump, which means 230 minus 218. We get 12 volt is given for the cable or for the wire. Now we need to find the resistance of the wire. We know according to the Ohm's law, V is equal to IR. So resistance of the wire is going to be voltage over the current. Voltage for the wire is 12 ohm. The current is going to remain the same as it is a series circuit. So the current is 0.83 ampere. So we are getting the resistance as 14.5 ohm. So this is for the entire wire, which is for the 18 meter plus 18 meter. So this resistance is for the 36 meter wire. Now the question is the resistance for 1 meter. So take this value of the resistance, divide by 36, you will get it as 0.40 ohm meter. So you can see here, take this 14.5 divided by 36, you'll get 0.40 ohm meter. The answer for this question is option A. Question 33. Cell X has an EMF of 2 volt. So this is cell X. It has an EMF 2 volt. Internal resistance 2 ohm. Cell Y has an EMF of 1.6 volt. Internal resistance 1.2 ohm. These two cells are connected to a resistor of the resistance 0.8 ohm. So this is the 0.8 ohm resistors. What is the current in cell X? Now we should know that there are two batteries connected to each other along with a resistor, but all of them are in series because the same current is going to pass through. So in that case, the current that passes through cell X is the exact current that's going to pass through the resistance as well as to the cell Y. Now as you can see, the positive terminal is not connected to the positive terminal of cell Y. So it's not connected to the negative terminal. So they are actually connected opposite to each other. So to find the total combined PD or the EMF, we need to subtract. So in case if they are connected together, so for example, so in this case, this is cell X and cell Y. In this case, you can add. But if they are connected opposite to each other, so in this case, this is X, this is Y, you need to subtract. So the value is voltage 2 minus 1.6, you have 0.4 volt. Now to find the current, we need to add the resistance, which includes you need to add the internal resistance as well. Internal resistance is the resistance of the battery due to the chemical present inside. So 2 ohm plus 0.8 plus 1.2. So that will become 4 ohm resistance. So I is equal to V over R. The voltage is 0.4 divided by 4.0. You will get your current as 0.10 ampere, which is your option A. Question 34. In the circuit shown, a light-dependent resistor LDR is connected to two resistors R1 and R2. The potential difference across R1 is V1, potential difference across R2 is V2. The current in the circuit is I. Which statement about this circuit is correct? This is LDR. We have two fixed resistors. We need to choose which statement is correct. When current I increases, the current I increases when the light intensity decreases. Okay, so let's say the current I increases. So when current I is increasing, current is inversely proportional to resistance. Resistance will decrease. LDR always works when intensity increases, resistance decreases, or when intensity decreases, resistance increases. Now here, since the resistance is decreasing, intensity should increase. But they have stated that the intensity is decreasing, so A is not the option. They have said LDR is an ohmic conductor. What is ohmic conductor? A conductor that satisfies Ohm's law. Ohm's law states when the voltage across the current is directly proportional to the voltage across the conductor is directly proportional to the current provided all the physical condition as well as temperature remains the same. So what they're saying is the voltage will be proportional to current provided all the physical conditions, temperature remains the same. But here this is not happening. So this is not an ohmic conductor. So in this case, what happened is the resistance remains same, but here you can see the resistance is decreasing, so temperature will obviously vary. So it is not an ohmic conductor. So B is not the answer. Part C, the PD-V2 increases when the light intensity decreases. Okay, now let's say that the light intensity decreases. If light intensity decreases, then the resistance of the LDR will increase. So when the resistance of the LDR increases, then the voltage of the LDR will increase too. Now, if you want to know this one, you can take the voltage of the LDR is equal to current into the combined resistance. For LDR, you have to take the resistance of the LDR. This is according to the Ohm's law. Current can be found as the e.m.f. divided by the combined resistance. Let me call it as RC. I can call it as resistance of the LDR divided by the combined resistance into the e.m.f. Let me call this as V. So into the e.m.f. Now, what I mean is when intensity decreases, resistance is increasing. Resistance of the LDR is increasing, which means the voltage of the LDR will increase. Now, since this e.m.f. remains constant, if one side increases, V1's PD and V2 PD should decrease. But in this statement, they have taken the V2 increases, which is incorrect. Option D, the ratio V1-V2 is independent of light intensity. Okay, according to the Ohm's law, V1 is equal to the constant current through the circuit into R1. For V2, it is IR2. If you divide this same current, so you get V1 over V2 is equal to R1 over R2 by cancelling both the currents because they are of the same amount. So you can see V1 and V2 is dependent on the fixed resistance of R1 and R2, but not the LDR. So it is independent of the light intensity, which is correct. Therefore, the answer for this question is option D. Question 35. A power supply and a solar cell are connected using a potentiometer circuit shown. So this is the solar cell and this is the power supply. The e.m.f. produced by the solar cell is measured on the potentiometer. So this is the potentiometer. The e.m.f. of the solar cell is measured here. A potentiometer's wire PQ is 100 centimeters. So this is 100 centimeter and has a resistance of 5 ohm. The power supply has an e.m.f. of 2 volt and a solar cell has an e.m.f. of 5.00 millivolt. So the e.m.f. of the solar cell is 5.00 millivolt. The power supply is 2.000 volt. This length of this PQ is 100 centimeter, which has a resistance of 5 ohm, and this point S to the P is 40.0 centimeter. Which resistance R must be used so that the galvanometer reads 0 when PS is 40.0 centimeter. So when the potentiometer slider is kept here, the galvanometer reads 0 volt, which means the potential PD across this PS is equivalent to this solar cell. So when you subtract, you get 0. So in order to find the voltage of PS in order to find the value of this resistor, you need to equate the voltage across the PS to 5.00 millivolt. Now to do that, first you need to find the resistance on PS. We know that PQ is 100 centimeter, which is equivalent to 5 ohm. So for 40 centimeter, you divide this value by 100, multiply by 4, multiply by 40. So first find for 1 centimeter what is the resistance, then multiply by 40 to get the value, which is 2 ohm. So the resistance for this value, resistance for this, that means RPS, is 2.00 ohm. Now the next step is to equate your values of the potentiometer. So if you want to find the value of the potentiometer, VPS, you need to take the resistance at RPS divided by the combined resistance, similar to the previous question, same equation, into the EMF of the power supply. Let me call the EMF of the power supply as V. So into V. As you can see, same formula. This will be equated to 5.00 millivolt. Milli stands for 10 to the power minus 3. The resistance at PS is already found as 2.00. So this is the part. The combined resistance here is you need to include the entire length, which is 5 ohm, plus the resistance, which is 5.00 plus R, into EMF, which is 2.000, which is equal to 5 millivolt. Now make R as the subject. So I've taken this term to the other side, the remaining term to this side. And then when I simplify, I get my value R as 795 ohm. So the answer for this question is option B. If you find this video useful, like this video, subscribe to Learners Club and press the bell button to get notified with new videos. See you in the next part. Bye-bye.